In this video, let's talk about Hatree Fock approximation. And what's important here is that if we have a situation where we are dealing with atoms having multi electrons, then it automatically becomes very complicated to solve the Schrödinger's wave equation. And Hatree Fock is one of the approaches that's utilized in solving the problems in which we have electrons. So we have more than one electron present in the atoms. And to start with, it was basically the Douglas Hatree who devised a method to solve the Schrödinger's wave equation for these multi-electron atoms, and certainly the starting point should be helium, and if we have to write down the two electron wave function for helium, we can write down it as the product of two wave functions. So if I start with psi as function of R1 and R2, and we can write down this as phi R1, phi R2. Where this R1 is the position vector for electron 1, and R2 is the position vector for electron 2. Now, what is important for interpretation here is that we can have the probability density, and we can write down say, for example, if I have electron 1 and I have electron 2, and if I write down the probability density for electron 2, say, for example, so I can write down it as phi star of R2 and phi of R2 and dr. Now, rather than trying to attempt to solve the equation in a single shot, what we do here is we instead convert this spatial orbital, or the orbital for this electron 2, into a classical charged distribution. So assuming this electron 2, now this electron 2 can be replaced by a number of electrons, and what we assume here is that this electron 2 can be chosen as the classical charge distribution, and that certainly applies an effective potential to the electron 1. So depending now that potential due to the charge distribution of electron 2, that will certainly depend on the separation between these two electrons. If I choose that separation as R12, so we can think of writing the potential that's being felt by electron 1 as I should write the effective potential felt by electron 1. So that effective potential, if I call that V1 effective, that's going to be integral of phi star R2 and 1 by R12 phi of R2 and dr2. So the potential that will be felt, that will be experienced by electron 1, can be given by the integral over this phi star R2 and phi 1, and this effective potential can be given by this equation. So this R12 is it's the separation between the classical charge distribution that's assumed for the electron 2 and the electron 1. Now, what is important here is that this effective potential is only a function of R1. Okay, so because if we go with R2 minus R1, this R2 minus R1, when we make an integration over R2 minus R1, what happens is that this R2 this R2 is integrated out. It's integrated out. Now, Uh, what is important here is that we look for a trick. We look for a technique, and what we do is once we go with the trick, then we have a one electron Hamiltonian for the electron one. So we have electron one and electron two, and this two is chosen as the charge distribution, and electron one, for electron one we can have a Hamiltonian for this first electron, and and uh, and try to see that how this approximation can work for the atom like helium. So we can write down the Schrodinger's equation for helium, and let's write it in atomic units. And what's that? I can write down this H1 effective R1. So we are writing down this Hamiltonian for electron 1. That will be minus 1 by 2 del square 1 minus 2 by R1 plus V1 effective R1. Now, this certainly is the kinetic energy part of the Hamiltonian, and this is the electrostatic interaction between the nucleus and the electron 1. And this term is the potential that's being felt by electron 2, the effective potential that's felt by electron 1 due to the electron 2. And certainly, if I correlate this, I mean, this first term is the kinetic energy of the electron 1, and the second term is its attraction to plus 2 nuclear charge. So this 2 is because of 2 protons in the nucleus of helium atom, and the last term is basically it's the averaged potential energy due to repulsion with the second electron, which is chosen to be the charge distribution. Now, what happens here is that the first electron only sees. This first electron will only see what it will see is it will see the average of the second electron. It will not see anything like instantaneous from electron 2 point of view. So that's what's the difference here. And we have an equation like that of hydrogen atom here, and we can think of H1 effective for electron 1 as R1 and phi 1 R1 coming up with the eigenvalues E1 phi R1. So we can catch the situation here in terms of the Hamiltonian for the electron 1, and the first catch that we have here is that we have to know the orbital, the charge density for the second electron before we can know the effective potential for the first electron. And what is important here is that we are only talking about the spatial coordinates here, and the two orbitals are the same. The orbital is same for electron 1, and the orbital is same for the electron 2. So what is important here is that if we know the orbital for electron 1, that should be the case. Knowing the orbital for electron 1 will automatically lead something sensible out of here. Now, this is what is important here is that we always are looking or making an iterative scheme. So what we do here is we try to guess out something and then substitute. And once we guess something and then substitute it, and then what we do is we calculate and then we finally iterate. And the procedure until the input and the output that we obtain are the same. Now, to understand this or to go with some approach, what we always do here is we make use of a trick. And what's the trick? We start with some phi 1 of R1, as say we start from A, and what happens here is that what we do here is using this, what we do, we calculate the effective potential. We calculate this V1 effective, and then solve the Schrodinger's wave equation. And when we solve the Schrodinger's wave equation, we come up with the next orbital. And what we get, say for example, we get H1 effective
R1 and phi 1a R1. And here what we get is epsilon, say epsilon 1 and phi 1a R1. So we guessed some phi 1 of R1. What we do is we calculate it, and then we iterate it, and we come up with a new orbital. And so what we have here is we have an improved orbital, and using this improved orbital by guessing some approach, and and using another state for it, say phi 1 b r1. And what we do, we do the same thing here, and we calculate the effective potential, and then solve the Schrodinger's wave equation for an updated orbital. So this is my updated situation here, right? And one of the two things can happen. So this process can go on, right? Every time we will have an updated orbital. So what is possible outcome of this is either our orbital that we have chosen, it converges to so that the n plus 1th orbital is identical to the nth orbital, uh, or the orbital that we get, it gets farther and farther off. So either it converges, or the results that we obtain, they diverge from the originality. And if it diverges, we say that the iteration that we have gone with, this iteration has failed. So while this is an interesting approach. I mean, how do we know that the orbital we get at the end is any good for the problem that we have chosen? And what makes an impact here is the variation principle. It's the variational principle. This variational principle helps us once again, in a way that the energy of the helium atom in this orbital approximation is normalized. So writing down the energy, E is integral say phi star of R1 phi star of R2, and then H and phi of R1 and phi of R2 dr1 dr2. So what's our Hamiltonian here? So if I write down the Hamiltonian, I can write for helium here is minus times 1 by 2 del 1 square plus 2 by R1. So this is for electron 1, minus times 1 by 2 del 1 square plus 2 by R2, then plus 1 by R12. Now, this Hamiltonian can break down. This Hamiltonian we can break this Hamiltonian into three parts. And the first part, say I call that zeta 1, and that will be integral phi star of R1 times minus 1 by 2 del 1 square minus 2 by R1, then phi of R1 dr1. And another part, say zeta 2, that's going to be integral phi star R2, and then minus 1 by 2 del 2 square. Here I have a correction, this should be del 2 square. Del 2 square minus 2 by R2 times phi R2 dr2. And then the third term that we will have here is, say, J11. So that will be the electrostatic interaction between the two electrons. So that can be written as a double integral of phi star R1 and phi star R2, 1 by R12, then phi of R1, phi of R2, then dr1 and dr2. Now, the last term that we have here, this last term is called the Coulomb interaction. because what it does, it certainly looks like the charge distribution repelling, repelling, showing a state of repulsion. So we can think of writing down we can think of writing down the energy eigenvalues as the summation of E is zeta 1 plus zeta 2 plus J11. Now, what is important here is if I write down the correlation energy here. So if I write down the correlation energy for helium, this EC refers to E correlation. That will be E exact minus E Hatree. Now, this exact can be experimentally calculated, or this exact can be theoretically calculated using some other approaches. Now, if I choose this, the values for E exact and E Hatree for the helium atom in ground state, so it comes out to be, say, minus 2.9037 EH. So minus times minus 2.8617 EH. So solving this, we get minus 0.0443 EH approximately, and using for EH, using the value of hydrogen, what we get here is that the value is nearly minus 110 kilojoules per mole. Now, the point is that although we can see here that this Hatree energy, it accounts for almost 99% of the exact energy. But the error that we are talking about, the error is still too large. And why is it large? Because it is roughly, this energy is roughly equivalent to the energy of a chemical bond. Now, it's very difficult to attain the accuracy, the exact accuracy of the problem. Now, the result that we have obtained here, it can be correlated with, say, for example, there's a marine, and this marine has a person on it, and if we have to account for the weight of this marine and the weight of the person standing in the marine, the weight of the person standing in the marine will not matter when you make the calculations. It's like that we have if I choose an example of the simple helium atom that we have here, the mass of the electron in comparison to the mass of the nucleus is extremely large. So anything that we are obtaining here as 99% of the problem is again filled with a lot of error. In the measurement of the energy that's associated with the electron. It's like this electron can be treated as a person standing in a marine, of whose weight is very, very large in comparison to the weight of this person, if we correlate this weight with the energy that we are talking about here. So even though the result obtained here is 99%, the error is again large, because it's roughly this energy is of the order of the energy of a chemical bond. Now let's talk about the spin. I mean, when we talk about the spin, we talk about the Pauli's exclusion principle, and we have always been talking about Pauli's principle when we talk about the spin that's associated with electrons. So what happens here is that the total wave function when we take into account the spin of the electron, the total wave function is asymmetric. It's asymmetric under the exchange of the two particles. If we exchange two particles, say particle 1 and particle 2, the overall wave function has to be anti-symmetric. And anti-symmetric means by exchanging the particles,
we have the overall wave function has to be negative. Now, if I start with some labels that will be used to distinguish the electron's spin state. So if I use, say, for example, psi of alpha as a function of x, y, and z, uh, so this this psi of alpha, uh, uh, this is psi of x, y, z, and alpha, and psi of beta is x, y, and z is psi of x, y, z of beta. So alpha and beta is basically the representative of the spin of the electron, and we can think about this alpha as plus half, or we can say plus h cross by 2, and this beta can be thought as minus 1 by 2, or minus h cross by 2. So uh, since there are only two values for this spin, so we can have spin up, or we can have spin down. So we can write down these spin functions as 2 by 1 column matrix. So we can write down them as 2 by 1 column matrix. So for alpha, we can use a column matrix of 1 and 0, and for beta, we can use a column matrix of 0 and 1. And if we take their complex conjugates, say alpha star, so if I have to write down the alpha star, that will be the row matrix 1 star and 0, and for beta it will be 0 and 1 star. All right. So what we are trying to do here is we are writing down the spin, and we write down the spin in terms of the column matrix. Now, if we think of taking the inner product, if we write down the inner product of alpha and alpha, so what we'll have, we will have 1 0 and 1 0. So solving this will give me 1 plus 0, that's equal to 1. So again, if I take the inner product of beta, that is spin down, what will be that? That will be 0, 1, and 0, 1. So this will be 0 plus 1, so that will give me 1. And finally, if I take alpha and beta, if I take their inner product, so what I will have 1 0, and then here I'll have 0 and 1, and I'll have 0 plus 0, so I'll get 0. So what it shows basically is that the spin pot is normalized, and the two states, alpha and beta, and beta are orthogonal states. These are orthogonal states, and let me use some basic index to keep track of which electron we are referring in our problem. We have two electrons, electron 1 and electron 2. So to keep track, what I'm assuming here is that this alpha 1, this indicates the electron 1 and spin up. Okay, so this is electron 1 with spin up, and automatically then the same convention will go with beta for spin down, right? So in this in the orbital approximation, we can write down this wave function. If I write down the wave function for psi 1 and 2, what am I going to write is 1s, okay, alpha 1, and 1s and beta 2, right? And since the electrons are indistinguishable, we cannot distinguish one electron from the other electron. We could equally write down that psi of 2 1 is 1s alpha 2 and 1s beta 1. All right. Now, either wave function is equally good. I mean, both the wave functions are correct, meaning neither one or any one of the two is good and the other one is bad. And that's not the way quantum mechanics works. That choosing one over the other, there's no reason for that, because both kind of situations are possible. So what instead we do in quantum mechanics is that we take the linear combination of both the functions. So taking the linear combination of
of the two things. So for that we write down, we understand that psi is symmetric of 1 and 2. If we have symmetric, we will have psi of 1 and 2 plus psi of 2 and 1, and we can write down it in terms of the orbitals. 1s alpha 1, 1s then beta 2 plus 1s alpha 2 and 1s beta 1. All right. So similarly, we can write down the asymmetric wave function as, say, psi a as 1 and 2, and we can write down this as psi of 1 and 2 plus psi of 2 and 1, and we can write down 1s of alpha 1 and 1s of beta 2 minus 1s of alpha 2 and 1s of beta 1. So the first linear combination that I have written down here, this is symmetric linear combination. That means if you exchange the two particles, there is no change in the overall wave function of that system, and this state certainly falls into the domain of fermions and sorry, bosons, and bosons have integral spins. And the second case that we have here is the asymmetric result. Now this situation is valid for the particles which are called as fermions. I mean, electrons are fermions, protons are fermions, and neutrons are fermions. So if you exchange the two particles, if you exchange the two fermions, the overall sign of the wave function changes. So we call this psi a is asymmetric. So the second one that I have written down is the asymmetric wave function, and the first one is symmetric wave function. And you can see we have not normalized these wave functions. These wave functions can be normalized, and only the anti-symmetric function that we have here, this anti-symmetric wave function, satisfies the Pauli's principle. And after normalization, we obtain this psi as so psi it's 1 by root 2 times 1s 1s alpha of 1, then 1s beta of 2 minus 1s alpha of 2 and 1s beta of 1. Now, what is important here is, and what question arises in our mind is that how do we handle a situation where we have 3, 4, 5, 6, 7 electrons, so that the wave function always changes sign if the labels of any pair of the electrons are swapped. If we swap a pair of electrons, the overall wave function, the sign of the overall wave function has to change, and for that we go into the domain of what's called as Slater determinant. And if we go back to the concept of determinants, let's have some review of that, and then we will finally try to write down the Slater determinant for many electron atoms. So if we go back to the problem solving in suppose we have a 2 by 2 matrix, and if we take down its let me assume that we have a matrix 2 by 2, and we have its determinant. Say if I call this x, y, a, and b, and if we solve it, how we solve it? Okay, so this we'll multiply the two. This is xb minus ay. Right. Now, let me swap the two rows. So let me write down a, b on the top and x and y at the bottom, and solve the same problem. What I'll get is a. So multiply the two. This is ay minus xb. So if I can have a common minus here, so what I'll get is xb minus ay. Now, if I see the results that I have obtained here, the second result is the negative of the first result. So that means if we have a determinant, and if we swap its rows, then the result of the determinant the result of the determinant gives us the negative at the end. And there is another important property of this determinant is that if the two rows are identical, the the determinant vanishes. So we can choose here a b and a b. If I choose it like this, I'll get a b minus a b. The two will cancel and I'll get 0. So if we have a determinant in which two rows are identical, the result of that determinant vanishes. And let me choose a 3 by 3 matrix. Suppose I have a 3 by 3 matrix. Say I start with a b c, say d e f and g h I. Okay, so we can solve this determinant. Okay, we can have this a out, so this is a times. So what is left is e, f, h, and I. Then minus b. Okay, this and this. This is df, gi. Okay, and then c. Okay, choosing c. So then plus c, de, and gh. This is h. Okay. So if we swap any two rows here, it will change the sign of the all determinant that we have, right? And if we have the two identical rows in this determinant, the overall value of the determinant is going to vanish. So using the idea of determinants, we would finally write down a Slater determinant for this closed shell atom, and assuming that this atom has 2n electrons. Let us assume that it has 2n electrons, and if it has 2n electrons, then it has n spatial orbitals, spatial orbitals. So to write down the wave function, say psi 1, 2, dash, dash, to 2n electrons, okay? So this will give me 1 by under root of 2n factorial. Okay, I can write down this, and then I'll write the determinant. So writing down the determinant is, say, phi 1 alpha 1, then phi 1 beta 1, then phi 2 alpha 1, and phi 2 beta 1, and so on and so forth. So it'll go like this. So what will happen here? I can write down phi 1 alpha 2, then phi 1 alpha 3, and so on and so forth. What I'll reach here is phi 1 alpha, how many electrons? 2n. So similarly, this will reach to phi 1 beta 2n. And this will reach to phi 2 alpha 2n. And this will reach to phi 2 beta 2n. And this will go on like this. And we can have the final term. So having this huge determinant, if we exchange the two particles, then the overall sign of this wave function is going to change. And if we swap any two rows of this n by n determinant, what's going to happen is that the sign of the overall wave function that we are going to obtain is going to change. So this is how we write down this Slater determinant for a multi-electron atom, and this determinant makes sure that if you have the exchange of particles in a system, this exchange will automatically lead to the change of the sign of the wave function. And with this, I would like to end this part of Hatree Fock. So, bye.